Good morning all. Let us discuss the determination of CD for Venturimeter. A Venturimeter is a device which is used for measuring the rate of flow of a fluid through pipeline. The basic principle on which a Venturimeter works is that by reducing the cross-sectional area of the flow passage and a pressure difference is created between the inlet and the throat. The measurement of the pressure difference enables the determination of discharge through the pipe. A Venturimeter consists of an inlet section which is followed by a convergent cone, a cylindrical throat, a gradually divergent cone. So this is the representation of Venturimeter. So this is the convergent zone, this is the throat part, and this is the divergent zone. A U-tube manometer will be connected at the convergent zone and at the throat point. So this is the flow direction. So the main aim of the experiment is to determine the coefficient of discharge of a given Venturimeter. The apparatus required are Venturimeter, U-tube manometer, stopwatch, collecting tank and a metal scale. The procedure for determination of CD for Venturimeter is, first we have to check the experimental setup for leaks, then measure the dimensions of the collecting tank, note down the breadth and length of the collecting tank, then note down the flow meter specifications. So once the inlet valve is fully open and allow the water to fill fully in the flow meter, make sure that the height of the mercury column in both the limbs are same. In case if it is not in a same, by using a valve, remove the air bubbles, then again close the valve, then note down the readings. Then slightly open the outlet valve of the flow meter, then observe the manometer limbs. Adjust it to get a steady pressure difference between the limbs of the manometer, then note down the corresponding mercury levels. Measure the time t to collect H, height of the water in the collecting tank. Then repeat the same above procedure for different flow rates by changing the outlet valve opening. These are the observation and calculations. So initially you have to note down the diameter of the Venturimeter at the inlet D1 in meters, diameter of Venturimeter at throat D2 in meters. With that you can calculate the area of the pipe section A1 pi d square by 4 and area at the throat section by using a formula pi d square by 4. Area of the collecting tank A can be calculated by having a data that is the breadth of the collecting tank B into length of the collecting tank. With that we can calculate the theoretical discharge, that is Q theoretical equals A1 into A2 square root of 2G HV divided by A1 square minus A2 square. Here G is the acceleration due to gravity, 9.81 meter per second square, and HV is a Venturimeter head, which can be calculated as H into Gm by Gp minus 1, where Gm is the specific gravity of the monometric liquid or a mercury, and Gp is the specific gravity of the liquid. So here Gm will be considered as a 13.6 and Gp will be taken as a 1. So actual discharge can be calculated by using a formula AR by T. With that we can calculate the coefficient of discharge CD. So CD equals Q actual by Q theoretical. So now let us perform the experimental conduction in the laboratory. Good morning all. So we have discussed the theory concept. So now let us discuss the conduction of Venturimeter and orifice meter in a laboratory. So this is a starter. So this is a U-tube manometer. So this is a orifice meter and Venturimeter setup. So both the experiments have connected to the same setup. So this is the collecting tank. So you have to note down the size of the tank, and this is the storage tank or sump tank. Since both the experimental setup is done through the same, firstly we have to open the Venturimeter valve. Meanwhile the orifice meter should be in a closed. So this is the Venturimeter. So initially we have a convergent zone. This is the throat, and this is the divergent part. So before commencing the experiment, so the pressure valve should be open, the Venturimeter pressure valve should be open. Meanwhile, the orifice meter pressure valves should be in a, and orifice meter the pressure head valve should be in a closed state. So this is a U-tube manometer. So both the side of the limbs should be in a level. So in case if the U-tube manometer limbs are not in the same level, by opening the valves you have to remove the air bubbles and you have to make the manometer levels in a same. After that you have to close the valve. So initially we can vary the discharges through the control valve. So this is the maximum discharge. So this is the medium discharge, and this is the for the low discharge. So here we'll do the conduction for maximum discharge. Switch on the starter so that the water starts to flow within the pipe. Then you have to note down the manometer readings. So this is the 0th level. You have to note down the initial reading as an H1. So initial reading you have to note down. So this one we'll note down as a H1, and above the 0th level the reading which it is showing in manometer you have to note down as a H2. So that H1 plus H2 you will get the total head. So after noting down the manometer readings, next we have to close the butterfly valve, and you have to note down the amount of water that has been collected in the storage tank for 0.1 meter rise. So you can start from anywhere. So here initially we are starting from 16 to 10 centimeter rise, so up to 26. Then after noting down the reading you have to open the valve. With that you can calculate the Q actual. So you have noted down the reading, that is the time taken to collect water for 0.1 meter rise in a tank. So the same procedure you have to follow by varying the discharges. By varying the control valve, you can note down the readings for medium flow. So manometer readings can be noted down. So similarly, you can note down the amount of water that has been collected in a collecting tank for 0.1 meter rise, and you can repeat the experiment for a low discharge, and you can note down all the readings, and further you can calculate the Q actual and Q theoretical. So with that we can calculate the coefficient of discharge. Conducting the experiment in the laboratory, this is the calculation part. So you can do for 3 trials with varying the rate of flow. So here first trial have been done for the maximum discharge. So these are the manometric reading. So H1, it is a right limb reading which has been noted in millimeters. We have got 150, and left limb reading as taken as a 165. So with that you can calculate the head, capital H, that is H1 plus H2, representing in terms of meters of mercury. So H1 plus H2, 150 plus 165, we will get 315 into 10 power minus 3. Here we are converting the millimeters into meters. So once the capital H, that is the head, is calculated, next you can calculate the Venturimeter head HV by using a formula H into Gm by Gp minus 1. So Gm is the specific gravity of a mercury, 13.6 divided by 1 minus 1 will get 12.6. So 12.6 into 350 into 10 power 3, that is multiply with the Venturimeter head, we will get the head as a 3.969 meters. So once the Venturimeter head is calculated, next directly substitute all the values in a Q theoretical expression and calculate the theoretical discharge. So here we have got 1.11 into 10 power minus 3. For 0.1 meter rise, we have noted down the time. So T we have got 12.318. So with that you can calculate the actual discharge, that is A R by T. So A is the area of the collecting tank and R is a 0.1 divided by T. So we have obtained 1.015 into 10 power minus 3. So with that you can calculate the coefficient of discharge Q actual by Q theoretical. So for the first trial we have obtained 0.91. So similarly you can perform for the other rate of flow, that is for a medium rate and for the low discharge. So finally you can have an average of coefficient of discharge. So you will get around the value as a 0.92 or 0.93. So this is experimental calculations. So with that we can give the answer coefficient of discharge CD. Thank you.